Okay, now, welcome back. For the very last tutorials of our fixed model Bayesian analysis, the thing that we are just going to do is that we are just going to do a simple and quick, I should say, predictive posterior check. Or PPC. In order to do that, we just need first of all to install the Bayes plot, and we have done that extensively and we have talked about that in the other courses. And now in order to do that, first of all, we have to just define, I should say, if you remember, if I just go to the posterior which we had, I should say, normalized whole brain volume replication, which it was essentially a matrix of 2000 rows, which is estimates for 373, I should say, the observation. And now the thing that we just want to do at this stage is that I'm just going to call it here again, normalized whole brain volume as a rep. I'm just going to go ahead and simply just write as matrix, because we need the objects to be done as a matrix. I'm just going to put the model A, and also for the second argument I have to just put, I should say, the parse, which is going to be the same thing that we created over there, which is going to be normalized whole brain volume rep. If I execute that line, I have one object which essentially is a matrix of all the replicated data which we draw from our posterior. And in order to see that how our model can just reproduce itself, we talked about that extensively with lots of visualization in the other course that we said, in the other course that I had. We say that, okay, it's going to be, I should say, PPC, dense overlay. We are just going to use this function. And now it's the matter of which I should say I'm just going to press F1 to see the help menu opens. You see that you have two objects you have to just put inside, I should say, as an argument. The first one is going to be your Y. What is Y? It's actually the observed normalized whole brain volume or response variable. However, what is the Y replicated one? The Y replicated one is the objects that I created it here as a kind of a matrix. And that's what I'm just going to just put it there. I just call that normalized whole brain volume replicated. However, that's going to be all the arguments which is going to be necessary in order to execute that line. The problem is that because we have almost a huge matrix, in order, if I just want to run everything, it's going to be computationally too expensive. Then as a result, I'm just going to subset some parts of the replicated model that I had. I say, okay, instead of having 2000, if you, for example, if you look at this one, if I just say dim, normalized whole brain volume rep, you see the dimension is going to be 2000 rows, which is going to be 2000 rows essentially, 373. I say that instead of 2000 estimates and draws, I'm just going to check from 1 to, let's say, 50 and put the comma, which it means that I take all the features of, I should say, observation of 373 observation. Then now it's not going to be as computationally as expensive as the other model, and the model is now ready to be executed by pressing Control Enter. Okay, it says that it's not fine normalized whole brain volume. I'm gonna put the data, take this one, execute the line, and it's gonna be executed now. You see, it takes a couple of seconds because it's somehow computationally expensive, and you see that the model which is created, I'm just gonna zoom and maximize the window, and you will see that the model that we had, the original model, is gonna be the one which is black. The model that is replicated based on the model that we proposed, it's going to be these, I should say, blue lines there, which essentially not a bad estimates and it has some kind of, I should say, closeness to the original data and the model that we had. Essentially, that was a concept that we just finished our tutorials with our single model Bayesian analysis. But however, before we finish, I just want to mention that we just got the intercepts of our model as 0.92 as the normalized whole brain volume of the person who are just 60 years old, and we notice that the slope, which is gonna, it shows that the how much the brain is gonna be in terms of its volume to be reduced after each year by this, I should say, this value there. The minus shows that the brain volume is going to be reduced, and this value shows that the amount that is going to be reduced after each year in our model. Okay, now you see that probably the model that we have created, it does not incorporate the variations that we discovered before, the variation if that person has a dementia or not. Probably think to yourself that, okay, the person who starts at the age of 60 may be suffering from the severe Alzheimer, then we should expect that its normalized whole brain volume, it's going to be much lower than someone who is a normal person coming to our clinics for, I should say, for the experiment. But the model that we have here, it doesn't look into these variations. It doesn't respond to you if the person in your clinic is dementic or not. What is its gender? Is it a male or female? What is his education level? Does he finish only the high school or he has a postdoc? And also, what is his social economic status? Or even if he has Alzheimer, what is the stage of the Alzheimer he's suffering? The model that we created here does not respond to any of these variations that we explored and discovered that in the knowledge discovery session of these tutorials. Then now, it means that the model that we have here, although can replicate its own, is not responsive to many questions that we have, and it cannot find any answers to all of these questions. Now, let's come back from the next tutorial. From the next tutorial, we are just going to answer one of these questions. And the question is that going to be, is the intercepts that we got and their slope is going to be different for someone who has Alzheimer or not? And we see that over there, the intercepts and the slope is going to be significantly different from the one that we have from our model here. Okay, I cannot wait to start the next tutorial because we are just going to start the very first model as hierarchical Bayesian model using STAN as a probabilistic programming in our analysis. Then I should say, I can't wait to see you at the next tutorial.